Hi,
People are coming.
Hi,
how you doing?
good,
Hello,
good.
Albany.
Good to see you.
Oh, hi,
Yeah.
hi.
Oh, hi, Wolfram.
Hi, nice to see you. So everyone meets in Mexico now. Very good.
Just 1 minute more, Kehe. Okay, it's a great pleasure for me to present Kehe Zhu from State University of New York at Albany. He will speak about a sister algebra of entire functions. Please, Kehe.
Thank you. It's really nice to see some old friends over here. I'm going to talk about something I did recently. Not like a major thing. It's a very small result, but I think it's a very interesting one. As far as I know, it's something that has not been done before. So hopefully this will generate some interest for future research. So I'm going to talk about the construction of a particular, say, star algebra of entire functions. And the main point over here is that this star algebra consists of analytic functions. The setting I have over here is the complex plane. So the functions I have will be entire functions. But the natural question is, can you also do something similar? For example, maybe on the unit disk, on the unit board, can you do something similar? Okay, so let me begin with the basic definitions of operator algebras. The starting point is usually the Banach algebra, the notion of a Banach algebra. So X, you say that capital X is a Banach algebra if number one, it is a Banach space, and number two, it has an algebraic structure on it, meaning that you can also define multiplication, and the multiplication and its norm is supposed to satisfy this inequality. The norm of x times y is no bigger than the product of the norm of x and the norm of y. And if the algebra has a unit e, then you also require the norm of the unit to be 1. So that's the definition of the Banach algebra. And then after Banach algebras, you usually define the star algebras. So you say that X is a star algebra if it is already a Banach algebra. So there's a complete norm, there's a multiplication. And in addition, there is a conjugation operation, which is usually denoted by X star. And that is why such algebras are called the star algebras, because there's a star operation over here. And then the main thing for a star algebra is that the star operation is supposed to satisfy 4 conditions. The first condition is that if you take the star twice, you're back to the original vector x. And the star operation, when you apply to a linear combination of 2 vectors, then it's a linear combination of the 2 adjoints, but the coefficients will have become complex conjugates. And then the adjoint of x times y becomes the product of y star times x star. And finally, if you wanted the norm of x star times x, then it will be the same as the norm of x squared. If it's for students over here, if it's the first time you see star algebras, the most important examples are if you have a compact space K, you look at all the continuous functions on the compact space K, that will be a star algebra. The linear operations are the usual linear operations. Obviously, you can multiply two continuous functions to get a continuous function. And the star operation on CK will be simply complex conjugation. Similarly, if you have a measure space X and you look at L infinity X, then it is also a star algebra. You have the usual algebraic operations, addition, scalar multiplication, and function multiplication. And the star operation in L infinity is also complex conjugation. So those are very typical function algebras. And another very classical example is if you have a Hilbert space H, and you look at the space of all bounded linear operators on H, denoted by BH, and then you have the usual linear operations. A linear combination of two bounded linear operators on H is still a bounded linear operator. Multiplication over here will be composition. So if you have two operators, S and T, you can do S times T. It simply means S composed with T. That's the multiplication. And then the star operation on the BH will be the usual adjoint of a bounded linear operator. Okay. And then they all satisfy the four axioms over here. The main difference between the three algebras over here is that the CK and L infinity are what are called cumulative C-star algebras, and then the BH is a non-cumulative C-star algebra. I also want to mention von Neumann algebras, although I'm not really going to talk too much. Von Neumann algebra is when you go one step further. You look at particular C-star algebras. Look at the C-star subalgebras of BH, and if the C-star subalgebra is close in the strong operator topology or equivalently in the weak operator topology, then you say you have a von Neumann algebra. And again, the main difference between a von Neumann algebra and a C-star algebra is that a von Neumann algebra, by definition, is a subalgebra of BH, and then C-star algebras do not necessarily come from BH. Okay. And of the three examples I just mentioned, L infinity is a von Neumann algebra. Well, a priori, this is not like a subalgebra of BH, but somehow you can think of L infinity as the algebra of operators. And what you do is when you have a measure space X, you look at L2X, that is the space H, and then you look at all bounded linear operators on L2, and then if you have a bounded measurable function, then the bounded function will induce a multiplication operator on L2, and the multiplication operator will be bounded. And this way, you can think of the L infinity as the algebra of all bounded multiplication operators on L2X. And so that's why people simply say that L infinity is a von Neumann algebra. Okay. All right. So clearly I'm going to talk about algebras of functions. And in classical analysis, I mean, function algebras have been studied for a long, long time. There are many good examples of function algebras. If you only want like a Banach algebra, there are many good examples. One very important example is if you focus on the unit disk D, you look at H infinity of D, the space of bounded linear functions on D. That's a Banach algebra. It's one of the most important Banach algebras in analysis. You can also look at AD, the disk algebra on the unit disk, meaning that you look at all continuous functions on the closed disk that is also analytic inside. That's That's called the disk algebra. That's also a Banach algebra. You have the usual operations of functions, and then the norm is the sup norm, and they become Banach algebras. Okay. When you study function algebras, people usually consider the star operation as the conjugation, as I mentioned earlier. Either you have like, you look at the algebra CK or L infinity, the star algebra is simply complex conjugation. But obviously, if you want to look at the classical examples like H infinity and AD, the conjugation operation will not be defined on those algebras, because when you have an analytic function on any region, and if you take the conjugate, most likely it's not going to be analytic again, unless the function is a constant. So the complex conjugation cannot be used in the study of Banach algebras like this to make them into C-star algebras, because again, the conjugation is not going to work. And that is why, as far as I know, all the Banach algebras of analytic functions so far, they are not C-star algebras, and nobody has really studied any C-star algebras of analytic functions before. And again, it's because the natural complex conjugation is not well defined on the Banach algebras. So if you want to study a C-star algebra of analytic functions, the first thing you need to do is you need to come up with the conjugation operation, a star operation. Now, if the underlying domain is a symmetric, very symmetric domain, like the unit disk or the unit ball or like the complex plane, meaning that if the domain is closed under conjugation, other than the complex conjugation, there's also a very natural analog of it. What you can do is you can define a star operation in terms of Taylor coefficients. For example, if I'm looking at analytic functions on the disk, you develop the function f into a Taylor series like this, and then you define the star of this function as this new analytic function. And then it is easy to check that the original function is analytic on the whole disk, if and only if this function is analytic on the disk. And in many cases, this operation will leave the space invariant. For example, if you have a disk algebra, if you consider the disk algebra, this operation is actually well defined on the disk algebra. And also, if you look at H infinity, then this operation is also well defined on H infinity. It is because the star operation can be written in terms of conjugation like this. You simply take the conjugate of z, and then you look at the fz bar, and then you take the bar again. And that's the new operation over here. And obviously, this operation will leave H infinity and AD invariant. And so this is a good operation on those two algebras. But the problem is, although this operation behaves in many ways like the complex conjugation, but there are several but it does not satisfy all the four properties of the C-star algebra definition. It turns out the first three operations are all okay. The fourth condition, if I use this as my star operation on H infinity or the disk algebra, then you can actually check that this fourth condition in the definition of C-star algebra is no longer satisfied. And therefore, you cannot make the H infinity and the disk algebra into a C-star algebra using this new operation. But at least we have like a candidate to try like on certain function algebras. And the algebra I construct today will actually, I'm going to actually use this operation, this as the star operation on the function algebra I studied today, a certain algebra of entire functions on the complex plane, and this operation will be well defined on that algebra. And for that algebra, this fourth condition will be true, and therefore you will get a C-star algebra of entire functions. Okay, but again, for people who like to try this, like maybe in the future, you definitely want to keep this in mind. This is a natural way of to define a star operation on analytic function algebras if the underlying domain is symmetric, because you want to take the z bar, and if z is in the domain, you want z bar also to be in the domain. So, for example, if you have the upper half plane, this will not be well defined. Anyway, so this is one of the key ideas over here. All right, so in order to come up with the C-star algebra of entire functions or analytic functions, the main thing is to number one, to have a star operation, which I just showed you that there is a natural thing to try. Sometimes it works, sometimes it will not work. In the case of the H infinity and the disk algebra, the star operation does not work. Another thing you need is an algebraic structure. Oftentimes, when you have a space of analytic functions, I mean, for people in this area, we have many Banach spaces of analytic functions. Bergman space, the Hardy space, many function spaces. You have a complete norm, but you don't have a multiplication operation like the Bergman space, the Hardy space. You do not have a multiplication. So you also need to define multiplication. If the space is not of L infinity type, usually the usual multiplication will not work. Okay, like if you have if you consider the Bergman space, when you take the product of two Bergman space functions, you're going to get out of the space in general. Okay, so multiplication is another thing you have to consider seriously. Okay, so the challenge over here is to come up with an algebra of entire functions with a certain multiplication, not necessarily the usual multiplication, and to come up with a star operation. And if you just want such an algebra, probably there are many artificial ways of doing that. I mean, if you're only trying to come up with an algebra, I have to guess there are many like artificial ways to do that. By artificial, I mean that in the following sense, in functional analysis, you know that any two Hilbert spaces of the same dimension, they're always like isomorphic. So probably you can use that idea to construct many C-star algebras of analytic functions just using some kind of artificial isomorphism. But if the construction is not natural enough, then the algebra will not be enough and will not be interesting, and you just get something that is useless. So you also want something that is natural. And what I present today is, I consider a natural algebra. Okay, it's going to be a natural C-star algebra of the entire functions on the complex plane. And my construction is based on the theory of Fock spaces. And the algebra I construct will actually be sitting inside the Fock space. So it's going to be a linear subspace of the Fock space. But of course, the norm is not going to be the original Fock norm. Otherwise, when you take the completion, it's going to get out of the Fock space. So the norm is going to be different. But as a set, it's going to be a subset of the Fock space. And the algebraic structure, I need to warn you first that the construction I have, the example I have today, as a C-star algebra, it is actually isomorphic to L infinity R, where R is the real line. So the algebraic structure itself is, there's nothing new over here. So if you want to get any C-star algebra properties out of this function algebra, you're not going to see anything new because it's just L infinity R. That's a very classical example already. And L infinity R is actually a one-nomen algebra. So the example I get today is actually a one-nomen algebra. But the as a set, it's going to be a subset of the Fock space, the Fock L2 space. And the linear structure is the same, but the multiplication will be new, and the star operation will be the one that I mentioned earlier. Okay. All right, so in order to write down this algebra, you need some basic information about the Fock space. So if you're not familiar with the Fock space, here are the basic definitions. Okay, C is the complex plane. HC is the space of all entire functions. And then on the complex plane, there's a very nice measure, the so-called Gaussian measure, denoted by d lambda. It's the e to the minus mod z squared times dA, where the dA is the usual area measure on the complex plane. So you use the Gaussian measure to construct a Fock space. You just look at L2 of the complex plane with respect to the Gaussian measure intersection with the space of all entire functions. And then it's easy to check that this is a Hilbert space. I'm going to call this the Fock space, although the term is not universal, not quite universal, although it is becoming universal after my book. People used to call this the Siegel-Bogman space, the Fock space. There are several different names for this. Anyway, I'm going to just call this the Fock space. It's a Hilbert space of entire functions on the complex plane. Oh, by the way, everything I do over here is also true. Like if you go to higher dimensions, if you move to Cn instead of C, all the definitions will be the same. All the constructions will be the same. But you don't really need any knowledge about several complex variables. You just work on the plane over here, and everything else will be naturally generalized to the higher dimensions. Okay, so as a subspace of L2 of the Gaussian measure, F2 is a Hilbert space, and it's also a separate Hilbert space. You can write down a very elementary orthonormal basis. Just use the monomials and make them unit vectors. So you divide Zn by square root of n factorial, denote this by En, then what you get is a orthonormal basis for the Fock space. And using this elementary basis, you can also calculate the so-called reproducing kernel of the Fock space, and it becomes this linear exponential function. Using this normalized reproducing kernel, you can represent the orthogonal projection from L2 to the Fock space as an integral operator. So all this is well known, pretty easy to do. And in particular, if you're interested in the theory of Fock spaces, you can look at my 2012 book, Analysis on Fock spaces. Everything over here is in that book. Okay. I mentioned earlier that in functional analysis, if you have two infinite dimensional Hilbert spaces, and if both are like infinite dimensional and separable, then the two spaces are always isomorphic. And therefore, doing operator theory on one space, theoretically, it's the same as doing operator theory on the other space. And in particular, over here, I now have two separable Hilbert spaces. The Fock space of the complex plane is a separable Hilbert space, infinite dimensional. I also have L2R, that's also an infinite dimensional separable Hilbert space. So theoretically, there are many unitary operators from L2 to F2. And when you say unitary operator, I mean a linear mapping that is one-to-one onto and preserving the norm. So operator theory on L2 theoretically is equivalent to operator theory on F2. And I keep saying theoretically because in practice, the operator theory on L2 is much different from operator theory on F2 because the kind of tools you have will be much different. And this is why there's some interest in doing operator theory on function spaces. For example, if you're interested in the so-called invariant subspace problem, initially the problem was raised about little L2, but in that context, it's extremely difficult to study invariant subspaces. But if you use an analytic function space like the Hardy space of the disk, then it's a lot easier to formulate invariant subspaces. And same with the Bergman space. Anyway, so sometimes there are good reasons to choose one Hilbert space over another just because you have new tools to use. So the operator theory will become sometimes easier or different or seemingly different. So this is a very classical example, okay, where you have two such different Hilbert spaces, and then theoretically you can look at the operator theories on the two spaces by using a certain unitary operator from one space to another. And again, theoretically, there are many, actually infinite many unitary operators from L2 to F2, but there's one particular unitary operator that has been studied for many years, I think over 100 years, and that is the so-called Bergman transform. Especially if you're like a student, you probably have not heard about this, although this is a very old object. So the Bergman transform is a certain unitary operator from L2R to the Fock space F2 on the complex plane. Okay, and you can actually write down the definition of the Bergman transform. It is a certain integral operator. If you have a L2 function on the real line, little fx, using this integral, you define a certain entire function. So the z appears inside the kernel over here, and what you get is the entire function. And if you denote the entire function by bf, then the bf is actually going to be in the Fock space. And of course, it's not clear, but it can be shown that the integral transform I defined over here is actually a unitary operator from L2R to the Fock space. Using this particular unitary operator, you see that the operators on L2R can be translated to operators on the Fock space and vice versa. Okay, and there are what I want to show you next is a few examples why I got interested in this like in the first place. I mean, when I was a PhD student at Buffalo, I already knew the Bergman transform. That was already used in the study of operators on the Fock space. I knew that, but I never really did anything until like 10 years ago when I picked up this tool again. I began with like several examples of this unitary equivalence. Okay, my first example is the Fourier transform. I think of the Fourier transform as a bounded linear operator on L2R. And if you know a little bit of Fourier analysis, you know that the Fourier transform is actually a bounded linear operator on L2R. Not only bounded, it is also a unitary operator itself. The term for that is usually called the Poincare formula. If you, again, are familiar with Fourier analysis, meaning that the Fourier transform maps a function in L2 to a function in L2, or at least a dense set over here to a dense set over here, and the norm is preserved. The L2 norm is preserved. So what I first computed when I got interested in this is that I think of the Fourier transform as bounded operator on L2, and I want to see what this operator will look like on the Fock space F2 after the Bergman transform. You remember the Bergman transform takes any bounded linear operator on L2 to a bounded linear operator on F2. So this is a bounded linear operator on L2, and what is its equivalent form on the Fock space. And the computation I did showed that the equivalent form actually is something that is very simple. So if I think of the Fourier transform as a bounded linear operator on L2, under the Bergman transform, I get an operator on F2, which I denote by F tilde. Then the capital F tilde is simply the operator. If you give me a function Fz, I get a function Fiz. That's the Fourier transform, the equivalent form of the Fourier transform on the Fock space. And after this calculation, I realized that the Bergman transform is really useful. Again, if you think about it,
maybe worth mentioning here that the Fourier transform in the phase space is rotation on P over 2. This is exactly reflected by multiplication by I in
Yes.
complex
Yes,
plane
yeah.
like a Fox.
Yes.
Like
yeah,
it.
good. Yeah. I mean, this example. I
space.
mean, when I computed this example, I thought it was new, but then I started digging the literature. Borgman already computed this like over 100 years ago. But not many people knew this, like in complex analysis. But once you see this new form, you realize the Fourier transform, why you have the Poincaré formula for the Fourier transform in the first place. From the new form over here, Poincaré's formula becomes obvious. You don't even need a proof, it's obvious.
Yeah.
Because f of z and f of iz, clearly they have the same norm. Because on the Fock space F2, the norm is L2 with respect to the Gaussian measure, and this Gaussian measure is clearly rotation invariant. And so Fiz and Fz clearly have the same norm, and therefore Poincaré's formula becomes obvious. And in the original form of the Fourier transform, Poincaré's formula is by no means obvious. The Fourier transform is not even well defined on the whole L2. It's only defined on a dense set. But in the new form, this operation is clearly defined on the whole F2. So that was the first example. And again, for people who just are interested in the Borgman transform, this is the first example you should look at. Okay. There are many other examples I computed in recent years. Another example that is very famous is if you look at operators on L2, how many operators do you know? I mean, I just showed you the Fourier transform. Another operator that is well known on L2R is the so-called Hilbert transform. Again, this is probably the most important example for people in harmonic analysis. So in harmonic analysis, there's the notion of the Hilbert transform in one dimension, and it also has a higher dimensional analogs. I'm not gonna write down the definition of the Hilbert transform for you. It is also itself is an integral transform, but the integral over there is not even a conventional integral. It's what is called a principal value integral. But in any case, the Hilbert transform is a very important example in harmonic analysis, and people have known it for many years that the Hilbert transform is also a bounded linear operator on L2. Not only is bounded on L2R, it is also a unitary operator itself. Again, that is a highly non-trivial result. And now if I use the Borgman transform to take the Hilbert transform to the Fock space, and after some calculations, a lot of calculations this time, the computation with the Fourier transform is relatively easy. But the computation with the Hilbert transform takes a lot of work. After calculations, I realized the Hilbert transform is equivalent to, as an operator, to this integral operator on the Fock space, where the integral kernel is the original reproducing kernel for the Fock space, together with a certain additional piece, phi of z minus w bar, where phi is a certain particular function I can compute. You don't have to know the exact form of this function phi, but it's something that you can compute, you can write down. It's an elementary function. Actually, it's an antiderivative of a quadratic exponential function. It is a function inside F2, but it's on the borderline, almost out, but it's still in F2. So you see that the Hilbert transform as an operator on L2 is actually unitarily equivalent to this integral operator on the Fock space. And once I write this operator down, I was very much impressed. An integral operator like this on the Fock space looks very pretty. I mean, at least it looks very symmetric. It's not exactly symmetric, but it's very symmetric. It's symmetric in the complex sense. I mean, you have a z and then you have a w bar. Inside over here, you have z minus w bar. The minus sign over here is not critical. I mean, you are going to see that a little bit later, I'm going to actually change this into a plus. You get something similar to the Hilbert transform. But again, the whole point is the Hilbert transform is unitarily equivalent to this integral operator on the Fock space. And the kernel you can actually write down.
Kehe, may I ask you a question?
Yeah.
Have you computed image on the Fock space of the Segure projection? And you know that L2 of R are direct sum of function admitting analytic continuation to the upper or lower half plane, and how this subspace is translated to the Fock space?
Yeah, that's a good question. I have not considered it, and I have not seen anybody computing it.
I think this is a very interesting question.
Sure, yeah. And also related to your question, there's another natural question. I mean, the Bodman transform takes L2R to F2, and a natural question is, what about LP? And then people have studied this problem. It does not take LP to FP. There's also a Fock space analog of FP. But the Bodman transform does not take LP to FP. So in terms of this idea, it only works for L2.
Mm-hmm.
Yeah. Anyway, so after I computed the Hilbert transform, I realized that integral operators like this are probably going to be very important in the context of the Fock space, and therefore I actually raised a question formally in 2015. I asked, okay, for the Hilbert transform, if I have a particular function phi that I can write down, this integral operator is actually equivalent to the Hilbert transform. But obviously, you can define an integral operator like this on the Fock space for many, many other functions phi. And my question was, can you describe all the functions phi such that in the Fock space F2, such that this integral operator will be a bounded operator on F2? I think it's natural to anybody who computed this will naturally think about this question. And so I actually formally raised this question in integral equations and operator theory in 2015. Several people worked on the problem. I even received a couple of solutions, but eventually the first 2 or 3 solutions sent to me were all incorrect. There's some mistakes. And then eventually in 2020, a group of 5 people, 3 of them are from China, Cao, Sheng, and Yan. Yan is a very famous harmonic analyst in China. Even in the internationally, he's well known in harmonic analysis. Brett Wick, I think most of us know. And Cao is a colleague of mine. I went back to China very often, and I collaborated with him several times. So they saw this problem, and they also started working on this like in 2019 after a few failed attempts by other people. And then in 2020, they eventually got a correct answer. And basically their result tells you that operators like this, integral operators like this, are bounded on the Fock space if and only if the function phi comes from L infinity of the real line in a certain sense. There's an integral transform, and they'll tell you exactly what kind of phi you can construct from the Fock space. And again, they come from L infinity of the real line, and such that this operator will be bounded. So it's a very it's a beautiful result, and it tells you everything about this kind of integral operators. And its bottom line is basically integral operators like this are kind of multiplication operators on the real line, not exactly multiplication operators. If you want it to be precise, their result is that integral operators like this on the Fock space are unitarily equivalent to the so-called Fourier multiplier operators on L2.
Mm-hmm, mm-hmm.
In other words, on L2, you have the usual multiplication operators. And if you use the Fourier transform, think of that as a unitary operator on L2, you use the Fourier transform to translate the multiplication operators, they become Fourier multiplication operators. And it turns out that the Hilbert transform is a typical Fourier multiplier operator. And so it turns out it's true in general. So operators,
it should be sign function for the Hilbert transform.
For the Hilbert transform, it's just Fourier, the sign function of the real line. And then it turns out you can use any bounded measurable function on the real line, and the multiplication operator over there in the Fourier form is going to be equivalent to something like this. And so, but again, there's a little bit of nuisance over here. Again, the counterpart you get on L2 is going to be not exactly the multiplication operators, but the Fourier multiplication operators. But once you realize that, then it's actually easy to fix it. So it turns out in this integral operator, if you change the minus into a plus, what you get will be exactly the original multiplication operators. So the first thing you can now do after that is you can prove the following result. Okay. So if you fix the function psi on the Fock space, you look at this kind of integral operators, where the inside now is z plus w bar instead of z minus w bar. Then this kind of multiplication operators are exactly equivalent to the multiplication operators on L2. So xi is unitarily equivalent to m phi with the Bachmann transform, and the relationship between psi and phi will be given by this integral transform. You can sit down and compute it, and once you realize this, it's relatively easy to compute, and this result also follows from the result I mentioned in the previous slide, the result of the 5-author paper. So you can think of this as a corollary to their result. But so what I'm going to talk about next will be formulated in terms of this. So the integral operators I have on the Fock space will be like this, and they are equivalent to classical multiplication operators on L2R. Okay. All right. Once you reach this stage, you already have a very interesting star algebra. Okay, and that algebra was already studied in the 5-author paper I just mentioned over here. If you look at this transform over here, it's going to send L infinity because phi comes from L infinity of R. This will send L infinity R to a collection of bounded linear operators on the Fock space. And that collection of operators using the Bachmann transform clearly forms a star algebra. It's a one-nomen algebra. And that algebra was already studied in this paper. But the trouble with this formulation is that the elements of the algebra are operators, and they're not functions. And if you're trying to construct a star algebra for analytic functions, you need to go from operators to functions, and that's exactly what you do for the construction of the example over here. You simply go from xi down to xi, and it turns out that is one-to-one. As long as it's one-to-one, then you're going to get a certain algebra of functions, which are analytic, and it's xi over here is clearly an analytic function. It's inside the Fock space. And therefore, the algebra you get today will actually be a subset of the Fock space. It's just a collection for all the xi's over here. Okay. Now, as a set, that's what you do. Okay. And the Banach space structure is also obvious. You simply use operator norms as the norm for xi, and then you're going to get a Banach space. And then the trouble over here is that the Bachmann transform is not multiplicative. So if you have like phi 1, phi 2, you do not correspondingly get psi 1, psi 2. You're going to get a new multiplication. And that is the computation you have to do next. How the multiplication for phi will translate to multiplication for psi, and how the adjoint of the operator, the multiplication operator, is going to correspond to, like at the function level, what corresponds to the psi over there. And then you have to do computations. And so here now is the details of the computations you will have to do. In order to show you the star algebra of entire functions, I first tell you what it is as a set. So as a set, I'm going to denote it by A. It's a set of all psi z. Bogman transform of phi z times e minus x squared. So if phi is bounded on the line after you multiply it by this is a L2 function, the Bogman transform will take this L2 function to a F2 function. So this is indeed a subset of the Fock space F2. Okay, as a set. This is going to be the A. This is obviously a linear set. You can do addition, you can do scalar multiplication, not any problem. So as a linear space, this is going to be this set together with the usual addition and scalar multiplication. And then you can show that this actually becomes a Banach space if I define the norm of psi simply as the norm of the integral xi. And therefore, if you write the norm of xi using the definition of norm, then the norm of psi is going to be simply this. Okay. The reason I want to write down this complicated formula over here is that eventually I'm going to present the algebra to you without the mention of Fock spaces. Everything can be just written down like just using the Gaussian measure, the usual complex analysis without going to operators on the Fock space. Okay, so I look at this set equipped with this norm, and again, in the background, this is the operator norm of xi. And then what you get is you're going to get a Banach algebra. It's just L infinity of R. I mean, you're getting a Banach space, L infinity of R with a complete norm like this. And then you're going to actually show that you can make this into a star algebra. And therefore, what you need to do is you need to somehow define multiplication and the star operation. And if you do, in order to figure out the new multiplication, this is the first application, the first computation I have to do. Okay, so if you have two functions, phi1, phi2, both bounded on the real line, and you look at the product denoted by phi, and you look at the integral transform under the Bogman transform. You're not looking at the Bogman transform of phi1, phi2 directly, but you have to multiply it by like an extra factor e to the minus x squared. Because when you have a bounded function, the Bogman transform applied to a bounded function, the result is not necessarily in the Fock space. But after this will be in the Fock space, and you can also do this. And then the relationship between the psi and the psi k is given by this integral formula. This just follows from some elementary result in several complex variables. It's pretty easy to show. But the trouble with this formulation is you have the z and the z bar in here. But obviously, if you let w equal to 0, then you're going to get a formula to compute psi z based on psi 1 and psi 2. Okay, and then you can show that the corresponding function psi, the function corresponding to phi 1 times phi 2, will be this function psi, the function that satisfies this condition. In other words, you're going to have an equality like this. xi is the same as xi1 times xi2. And again, if you set w equal to 0 in the computation over here, then one way to compute the new psi from the psi1, psi2 is using this integral formula. Again, you don't have to use Fock space. This is just a very elementary integral formula. Obviously, if psi1, psi2 are in the Fock space, you get an entire function, and you can check this entire function is still in the Fock space. It's not obvious though. Okay, if psi1, psi2 are in the Fock space, obviously you get an entire function, but it's not clear why the psi is still in the Fock space. But if you know this came from this calculation, then you know that this is actually still in the Fock space. All right. And then I've now got a set. I have a norm. I have a multiplication defined on that set. again, in the background, I know where everything came from, okay? And then I also need to define the star operation. The operator level is obvious. So if xi star, it's the usual algebra of operators, and it is going to be simply this. And now if you use the star operation I mentioned earlier, psi star defined using Taylor expansion, okay? It turns out it's given by this integral formula. And then it turns out this star operation will actually work in this context. Remember, this star operation does not work for the disk algebra. It does not work for H infinity. But luckily, it works for this particular context. And of course, I know it works because everything came from L infinity. Okay, so now I've got everything, all the pieces. And if I put all the pieces together, then what I get is the following result. Okay, so I define a set A consisting of all functions in the Fock space psi such that this is finite. And this way I get a subset of F2. I've got a norm. This is obviously norm. And if you want to check this norm directly, you can probably show, not too difficult, you can show directly that this is a complete norm. And therefore you're going to get a Banach space. But I don't have to check that. I knew this came from L infinity. L infinity is complete, and therefore the space, the Banach space I get over here is going to be a complete space. It's going to be a Banach space. So I've got a linear set, a norm, and then I claim that the A over here is actually a star algebra. So in a star algebra, you need the linear operations, which will be the usual addition and a scalar multiplication. You need a multiplication, and the multiplication is defined by this integral formula. And again, if you want to check this directly, it is also non-trivial. If you are given two functions, psi1, psi2, satisfying this condition, it's not exactly clear why this new function will also satisfy this condition. But again, because I knew this came from L infinity on the other side, and it corresponds to multiplication on L infinity, so I know that this will work. And its norm is defined like this. And again, on a star algebra, you need a linear structure, you need a multiplication, you need a norm. And finally, you need a star operation, and the star operation over here is given by this natural star operation without referring to the Fock space at all. And then the result is that what you get over here is indeed a star algebra. Again, the proof is free. You don't really have to prove everything as long as you know where everything came from. This multiplication came from the composition of the two integral operators I mentioned earlier, and everything came from L infinity. And therefore, what you get over here is indeed a star algebra. Not only is it a star algebra, it's also a one-normal algebra. Okay, so and if you the precise isomorphism from L infinity to A is this. If you have a function on L infinity, or you look at this function, it's going to be an A, and then this will be a star algebra isomorphism. The multiplication for phi corresponds to the new operation, the new multiplication over here, and the conjugation for phi corresponds to this. This way I get a star algebra of entire functions. Again, if you know the background, the whole thing is very simple. If you don't know the background, then if you simply look at this theorem over here, it is actually, there's a lot of work to be done. If you want to check this directly without using the Bogman transform, if you want to prove that this result over here directly, it's going to be a lot of work. Okay. All right, I want to mention a little bit more about so obviously in terms of algebraic structures, the main thing over here is the multiplication. Linear structure is the classical one, and also the star operation is the classical one, so everybody knows this. but multiplication is something that is new. And I want to say a little bit more about this new multiplication. Obviously, this multiplication can be extended to a larger set than the A over here. If you just want to define this new operation, you can extend it. If I extend the set A to a larger set, by larger, I simply mean that when that multiplication is well defined, then you get a much larger set. You may even go beyond the Fock space F2. At this point, I don't know exactly how large a set you can use to define this new multiplication. I don't know yet. I know you can go beyond the algebra A. I want to show you a few examples. First, I want to show you some bad examples. First of all, in terms of membership in A, so what kind of functions are in the algebra A? I mean, earlier I showed you the definition is kind of complicated. It turns out membership is not easy to determine. The first remark I want to make over here is that I assume everybody knows the notion of the Bayesian transform. For the integral operator xi, if you calculate its Bayesian transform, it is going to be just psi of z plus z bar. Very easy, okay? And so if you know that a psi is a bounded linear operator on the Fock space, that's exactly the same as membership for psi in A. A necessary condition is you need psi of z plus z bar to be bounded. And it turns out this condition is not true for most of the good functions. For example, if you have a polynomial, if psi is a polynomial, unless psi is a constant, this is not going to be bounded on the complex plane, because this being bounded on the complex plane means that the psi will have to be bounded on the real axis. Not every polynomial is going to be bounded on the complex on the real axis unless it's a constant. So automatically, the algebra A contains no polynomial. So it's a very abstract algebra. But it does contain a few elementary functions. If you calculate xi for functions like this, linear exponential functions, then you can actually compute that the integral operator I defined earlier is actually a so-called while unitary operator together with the multiplication operator. The while operator is a unitary operator, so in order for this to be bounded, the multiplication operator has to be bounded. But on the Fock space, there's no non-trivial multiplication operator. So in order for this to be bounded, the a plus a bar has to be 0. That means the a has to be purely imaginary. So you see that a linear exponential function like this belongs to the algebra A if and only if the constant a is purely imaginary. So you don't get a lot of linear exponential functions, you only get some very special ones. And in terms of elementary examples inside this algebra A, those are the two things I can say. So it does not contain polynomials. It contains some linear exponential functions, but not all. But the new multiplication actually is well defined whenever you have polynomials. So if I again look at this multiplication, it can be defined for any polynomials psi1, psi2, and this integral transform can actually be written in several equivalent ways. One equivalent way is this, and again, there are several other ways. Anyway, I want to show you that if you just want to have some feeling about this multiplication, I want to show you a few examples. Okay, you can extend this operation to a much larger set, a tilde, containing all the polynomials. And if you compute multiplication, this new multiplication, also this a tilde will contain all the linear exponential functions. If you compute EAZ times EBZ, it is the usual multiplication. The usual multiplication will give you e to the a plus bz, but you get an extra constant, EAB. And if you do z times z, you get the usual z squared, but you have a constant 1 coming up. And if you do z times z squared, you get the usual z cubed, but with a multiple 3, and you have another linear term. In general, you can show that if you have two polynomials p and q, you can perform this multiplication, you get a polynomial p times q. It's going to be a polynomial of degree n plus m. But if you want to compute it specifically, it's very complicated. I mean, you can imagine in situations like this, it's already pretty complicated. So the multiplication operation over here, I consider something interesting for people in complex analysis or functional analysis to understand what this new multiplication really means. Also, a natural question is, can you find the maximum algebra A tilde such that this operation is well defined? I mean, at this point, I don't know what this A tilde is. I know it contains all polynomials, it contains all linear exponential functions, and many other elementary functions you can write down, like sine, cosine, and so on. But exactly what is this maximum possible algebra? So certainly there's additional work people can do concerning this very abstract algebra of entire functions. Another natural question is, okay, I've now got this example of historical algebra of entire functions. Can you do something similar, say, on the disk? Again, I'm asking for relatively natural examples of historical algebras, okay, not artificially constructed. All right, I think that's all I want to say.
He may return to the previous slide.
Yeah.
Do you figure out which function correspond in a real line to the function z on the Fock space?
Yes. That's all computed in my book. Actually, all the monomials on the Fock space correspond to, on the real line, the Hermite functions. So if you look at z, it's the Hermite h1, and the constant function 1 in the Fock space corresponds to the Gaussian function e to the minus x squared, and so on.
Okay, thank you.
Yeah.
Thank you for a very nice talk. And now, question, comments, whatever.
Thank you, Professor, for your talk. Can you show again this condition? Something should happen to be finite, right? In order to have this space A?
Yeah, so the space A is the set of all psi such that the A psi is a bounded integral operator.
All right, okay. So how do you define the norm in this space?
Just use the operator norm.
Okay.
So this is the how you define the norm on top, but that's exactly the operator norm of A psi.
Okay. So when you mention how to extend this space, how to extend it, it should be
the norm. You cannot use this norm. If you use this norm, you're not going to get.
There should be another norm.
Well, the first thing to do is to just either get the maximum set A tilde such that maybe a linear space, such that on that linear space this is well defined.
Okay.
So this way you're going to get an algebra, but it's not a Banach algebra. You don't have a norm on it.
Right. Okay.
Yeah.
Very intriguing.
Yeah, it's a new operation. To understand this new multiplication, I think will be interesting.
Yes. Thank you.
Yeah.
Thank you.
Wolfram, would you like to ask something?
It's gone.
So, any more questions or comments?
The
Yeah, there's bad
So
connection.
the disk, if you take the
Yeah, the
Mhm.
connection is not good.
We cannot hear. Nikolai, who is asking?
Yes. Yes, I'm here. Can you hear me?
Yeah,
Yes, yes, but someone is trying to ask.
yeah, it's
Um,
Estella who is asking, but we cannot hear him.
Ah, Stella. Ah, no, but she's the manager.
Oh, okay.
More question?
so can I ask a question?
Yeah,
So if you look at the product, there is the reproducing kernel inside and somehow a shift.
yes.
So if you are on the disk and you replace the reproducing kernel by the Bergman kernel and the shift by the Möbius transform, for example, do you get anything reasonable then?
Yeah, the something very nice to try, but I don't know what you'll get. No, I have not tried anything on the disk.
I see. And the next question is, if you now have not just one Gaussian measure, but the usual family of Gaussian measures with some semi-classical parameter, then you get a family of products, right?
I mean, what I'm sure is that if you look at the e to the say minus alpha mod z squared, everything works. But other ways,
Yeah, but what happens if alpha goes to 0 or to infinity?
yeah, the
But the
other
product,
ways, I don't know. I never tried.
what happens to the product? No, I don't know.
Yeah.
So something about semi-classical asymptotics.
Yeah, I don't know.
Okay. Okay. Thank you very much, Kehe, for very interesting talk.
Thank
And
you.
this is the last talk for this semester. So we will see all of you in January.
All right,
And
thank you for having me, and I want to
yeah,
say
Merry Christmas and Happy
Merry
New Year
Christmas,
to all
yeah.
of you.
okay,
Happy New Year.
yeah.
Bye-bye. Thank you.
Yeah, thanks a lot.
Bye.
Thanks a lot.
Bye,
Nice
bye.
talk.
Estela, no vayas a desconectar.
Okay.
Es que vamos a quedarnos con el profesor